The talk is, I titled this talk Generative Opportunity. It was originally going to be about the internet, but I realized the internet itself is part of a much larger story. It's how software allows us to create new opportunity and work around problems. And the internet is simply one byproduct of that. So to give you an overview of it, we really want to create value by not just creating solutions and services, which is traditional what people sell, but want to create opportunities and the ability to discover what we didn't anticipate. And we need to think about systems as a whole, and not just layers and layers where we pile up depending on other people doing things, but the new engineering paradigm is resources. You look at everything as a resource. What can I do with it? What are the opportunities it opens up? And voice over IP is a good example. Rather than defending a telephone network, we create our own solution. And rather than providing solutions from a center, from providers, we want to see how our individual efforts can composite, form a whole. And this is really the magic of the internet. How we take millions of individual efforts and create something that's seemingly the web. There's not the web as a single thing, but as a result of what we do. And at the end, there are some policy takeaways. And as soon as I sneeze, if I sneeze, you'll know it. In any case, there's some policies takeaway. Basically, one of the simplest is how to create more opportunity by having infrastructure. Here we talk about infrastructure for IoT, for connected things, but the infrastructure to enable our efforts to be connected. And the other part of it that's less obvious to people is not just smart things, but APIs, program interfaces. How do we make it possible to build on top of all these capabilities and services? So, as I said, the internet is an embodiment of what we can do with software. The web and social media, or what do people think of the internet, of course? They think of it as the web and social media. They talk about access to high-speed broadband. These are all the popular ideas of what people think the internet is. And the latest, of course, being the Internet of Things. But, you know, it's sort of like the blind man and the elephant. Everybody has their idea of what the internet is. Some people think of it as electricity, something that consumes, something that's in pipes, something could be stolen. Or they think of the internet as a place you access, a place you go to, as a shopping mall. So let's take, try to understand really what the internet is and how we got there. But first, we hit a wall. And in Mumbai, this is the wall I hit here. We get other things. You have to know passwords to access. So your devices can't just connect. And this is the point I was going to make, about infrastructure. If we want more internet, how do we make more available? And Mumbai had another problem. They only opened up port 80. They didn't even give us the internet. So basically, my view of the internet is based on sort of a reality check. So this is inside my house, and as far as I'm concerned, this is the internet. I'm using IP protocols, the same internet protocols, a full browser to access a device that's within my house. And that is every bit as much of the internet as everything outside the house. But the big difference is that the browser is running in a device that's very powerful, but its capabilities are tuned and locked down for a certain use case. So that's the problem with use case. Whereas the device on the right, I can make into much more capable of making to what I want. So I can run wires to it, I can flash those bulbs. That's a full computer. It's even running a version of Windows. So one of the points I'm going to make is to try to remove the mystery of what's inside the devices. And I'm going to talk more about that this afternoon where I go into detail. But you'll notice the blinking lights in the browser are following those blinking lights. So this is a very different view of what the internet is. So if we look, if we talk about it in terms of creating opportunities, the internet is not the first example of generative opportunity. Steam engine, the railroads were, in a sense, the internet of their time in terms of an exciting new technology that people can build on. And telecommunications, when you first get telegraph, telegram, telephone, those all created new opportunities. So we tend to think of the internet as the first great new. No, this is a pattern we've had before. That's why it's so important to understand what it is and what the concepts are. The other big thing, and perhaps more important than the internet itself, are the concepts behind the internet. Just as writing and agriculture transformed the world, not so much the sort of the hours of labor, but the idea that you can do agriculture, the idea that you can share ideas by writing. And the term for some of this is a paradigm shift, change in how we think. And one of the classic paradigm shift is from Ptolemy's solar system, which had all, if you look at that, again, it's very complicated. The planets all going in orbits and epicycles. And then Copernicus simplified it by simply observing that if we just had a different perspective, just thought about it differently, he created something that hadn't existed before, the solar system. And that gave us physics and other insights we built on. And it empowers us, rather than, the solar system wasn't just a solution, it empowered us to create our own solutions. So let's look at how the internet happened to understand what it is and where it could take us. So standard history of the internet is people invented packet networks. And then there was the ARPANET research network, this nice, well-structured history. And then it became the internet. But that's not how it really happened. It happened in a sense by accident. We stumbled across it by programming around problems we had. And that's discontinuity. In other words, old telecommunications were layers. We programmed around the problems we had to create our own solutions. Again, I'm going to explain this in more detail. So we start with basic raw materials. We have copper wires, we have radios, and we have to discover what we can do. So the internet was a very powerful dynamic and allowed us to treat the entire telecommunications industry as wire. But first we need to understand how telecommunications works, what it is. Telecommunications builds on a tradition of communication service. We've had scribes and messengers for thousands of years before. But the telegraph was a key point. It gave us telecommunications, and basically a much more direct connection over distance using technology. Now, telegrams work sort of like freight on a train. You can tell I gave the talk in Mumbai by the example of Hello World, which is apparently pronounced similarly in Hindi. Am I correct? I just wanted to get a check. And it's all well ordered. The business model is like freight. And the carrier has to preserve the meaning. Now, what do I mean by that? Well, if we look at Morse code, and this room, some of you at least know what Morse code is, ones and zeros, you have to know what the language is. These are Morse code, standard Morse code, you know these are English letters. You share the same dictionary. And you get error correction because you know the English words. If you did Hindi, you might not be able to do error correction. Matter of fact, it's like people on Siri will discover error correction, or you're turning it back into English. So this is, and that's why we essentially had to build a separate infrastructure for each video, for each language, for each purpose. And that's classic telecommunications. Each of those infrastructures add value because they carefully preserve the meaning or TV. And it was a business carrying message just like scribes, and that was a valuable service. So we discovered digital communications because telegraph was digital. We were able to repeat the message over distance. The problem is telephony was analog. So the solution to analog was digital sampling. We took that analog signal and turned it back to a digital signal. And that's the basis, basically, for a lot of the communication sciences that the Communication Society does is based on this idea, digital sampling, but it was the same business model as traditional telecommunications, telegraph. And we invented the terminology which confused people. We use the word information for entropy. And that confuses people. They think it's about what people say. We talk about communications when we're really talking about transmission. It sounds like everyday language, but the meanings are different. And you know, it's as if we confuse the word work in physics with the word labor in everyday language. We don't confuse those. We know when a physicist talks about work, he's not talking about labor. So we had a different tradition once we got computers. We did use the telecommunication infrastructure. We used modems so it can basically send messages pass through a phone wire as if they're phone calls. And teletypes basically use modems so it can connect to our computers. And then we built access networks. We were doing all this stuff on our own with computers. It's totally outside the ARPANET tradition because in the commercial world, people are creating their own solutions. And we also had to start to interconnect our computers. So though the ARPANET might be the best known, it was not the only effort. But it was important because it made people very aware and put research money into it. Problem is the ARPANET was modeled on telecommunications. The network was responsible for keeping the message intact and carrying it. So it was still a service. So we discovered a different approach when we had packet radio networks. With packet radios, there was no provider in the middle to make corrections. So whenever a packet got lost, we had to basically retransmit or correct it ourselves. But this is the key. Software, we could program around it. It was no big deal. Basically, I want to send a message. I didn't get acknowledgement. Send it again. Very easy. You can time it out. If you don't want to wait forever, you can wait forever. But we also discovered, like, if you wanted the most recent temperature, you don't retransmit, just send the new temperature. So we started to explore this new space of opportunities. And it's totally outside sort of the frequency paradigm because they're packets. So Ethernet is basically nothing more than a packet radio on coaxial cable. Because it's at least classic Ethernet. Today Ethernet is very different. We tend to preserve the words. I won't go into signal processing, but classic Ethernet had the same problem, same algorithms as AlohaNet. And the reason it was a coax, by the way, was to avoid dealing with the FCC. But here's another important point. The software makes that cable, piece of copper, act like a network. It's not a network. It's not a layer we built on. It's a wire we use as a resource to do networking. And there are other networks like Token Ring, but I view Ethernet as a classic because it's so simple. And there's an irony, as the Wi-Fi has returned to wireless, we're now reversing the paradigm. But the key thing about both the AlohaNet and the Ethernet and any of these networks is you have packets that don't have meaning. Classic telecommunication network knows the packets are all in a stream. If you lose a packet, it knows the context. It can repeat it, but it's just taking responsibility for delivery. Here, nobody's taking responsibility. A carrier in the middle can't retransmit the lost packet because it doesn't know it was lost, doesn't know what the meaning is. That's why we need a different approach. Now, when we extended this into networking, we couldn't just retry. TCP is a more sophisticated protocol, but the basic idea is we have to take responsibility for solving problems outside the network. Now, the other big key idea is architecture. How do you design systems? So the important thing about the internet is you have an architectural boundary, is that it looks, and the reason it's confusing, it looks like layers. So we might call with TCP a subroutine that will reliably transmit just like the network provider did. But the difference is that software that we own and it's treating the wires as a resource. So the abstraction of layers, it seems simple because somebody's taking care of it, we don't have to think about it. With architecture, it looks similar, but what we're doing is partitioning the problems to keep things very simple. And again, this is why we can assume reliable connection, but we know that it's just a protocol, it might fail, might not be able to get through. If you're in this room, you can't make a connection. So we know enough that we don't overly depend on it. And this is why I use, for example, OneDrive or Dropbox keeps a copy of my machine. So even if I'm not connected, or even if I do what I just did, what did I just do? You learn how to recover. Let's see if I recover. Okay, slideshow. You might not have a choice. Don't worry. When you go back home, you'll see plenty of it. Okay. So now we're going to go directly to the slide we need. Yes. Let's see, different approach, Ethernet. Okay. Here we are. This is faster. You see, I'm able to create my own solution here. Of course, I created my own problems, which is part of the risk you take. So the way we got to the internet, as I said, we extended connectivity by to get into networking. So we had a lot of local networks. We had Ethernets, we had commercial networks, and the key thing is how do you connect them? How do you do the internet working? And the traditional way was you build a video connection, just like a new format, a new network for MP3, a new network for HDTV, a new network for each. Instead, they accepted the lesson of packet networks, basically like the Aloha Net, and said, what if we just exchange packets and we don't solve any problems in the network and make no promises? That's very counterintuitive. Because all networks have to do all these things. They have to make sure reliable delivery. They have to worry about unique address. They have to worry about this. And the answer is, we can't. All we see are packets. So that's what forced a very different approach. The real genius of the internet was accepting that restriction and saying, if you want to do a video stream, you take responsibility in the program, in the computer, to make sure that video gets through. And there are clever solutions, which sometimes you just buffer and you wait, that's lousy. Sometimes you dynamically change the resolution. The clever you are, the better you can do. But that's very liberating. That means we can reinvent everything. And one of the big challenges, though, is how do you share a congested medium? Because, you think back to the 1970s, when 56 kilobits was high speed. Unimaginably fast, because it was better than the 100 bits per second I was used to. But so things became congested, and the reason it's called Transmission Control Protocol is that it controls the transmission. So you don't send characters basically into a network that's already full and just keep jamming it up. Instead, if you basically not getting through, you back off. You adjust your speed dynamically. And this is a very powerful idea. But it's, again, a lot of this is counterintuitive because traditional networks, you assume everybody's going to behave badly. The network operator has to manage it and everything. And it turns out that the efforts to make the network better in traditional telecommunications terms makes it worse. There's a thing called buffer bloat, which buffering the network. And if you do buffering in a classic network, it makes it better eventually. In the internet, you lose the feedback you need to make TCP work. Everybody keeps throwing things into the network, the buffers fill, and on a gigabit network, a gigabit buffer is going to take a second to empty. A 10 gigabit buffer, which is cheap, could take, you're starting to get to minutes of delay because you lied to the user because the network thought it was smarter than the user. So this is sort of why putting smarts in the network backfires. We can't fix problems in the network. So let's give a more concrete example of how the internet works and why it works. So let's look at how fax and television work. You scan the image line by line. You send it across, oops, let me go back one. Okay. I need to get out my pen. I lost my pen. You send each one in perfect time across from the transmitter to the receiver. You put each one on the train, exact timing, and it works. And I mean, it's amazing we got television to work in the 1930s because you need microsecond timing. And they got that to work in the 1930s. So that was an amazing feat. And they deserve credit for that. But it's a little while ago. We moved on. So let's look at how we do this in software. Okay? We take, we tag each element of an image instead of just scanning it across. And then we can send them in anywhere, just throw the packets. And then as we see them, they come together and form an image. That's very different, very asynchronous, loose, very, very different. We don't depend on the network now because we know the packets are tagged and we can retransmit, we can make up for those packets. Now the big surprise is that this works for voice. It was not supposed to work for voice because everybody's told, every ears are very picky, you gotta get precise timing, everything has to be done exactly right, just even more than television. Turns out we can program around that. That's the theme here. And we're forced to by economics because the reason the internet could not do voice is that the packets are anonymous. You don't know who they belong to, what they mean. So you can't pay somebody to treat some packets better. Some people think you can, differential services or all these things, but the mechanism for doing that is much more complicated. And you can't even define QoS because what's quality for one application is not for another. This buffer bloat is a great example. Buffering is high quality until it's not. But what happened, but at some point, the web happened. We got capacity to do video, and demand created supply. Now, I know people talk about the more demand there is, less supply, the price goes up. That's not true. In the real world, if somebody's buying something, you will get the more of it. And when they're buying a lot of it, you have a Black Friday sale. And, and you can't even, how do you use up the internet? It's just a way we do things. But what accelerated is cleverness. Skype didn't wait for standards or things like that. It programmed around it. Use clever algorithms to program around telecommunications. So I discovered that Skype worked better than voice did. I could even was even able to do Skype over an audio line to Australia. When my beta son was there, I was able to use Skype to talk to him, just to try it, and it worked. In other words, you took a phone line, put a modem on top of that, then you put Skype on top of that, it actually worked. And turns out, once you discover this technique and capacity was created by the web, we got video. But you only got video because we accepted the risk. Sometimes it doesn't work. If we accept that risk, we can take advantage of the opportunities. And if we're resilient, instead it just doesn't break. The video might be a little less. Maybe sometimes we just get voice. That's what we get for taking responsibility and accepting the risk. And the magic is the voice had no additional costs because we're not paying anybody in the network for favors. We're just taking advantage of the opportunity. And this is why today cellular is moving to Wi-Fi. Now they're trying to keep you convinced we need a cellular phone company. Just like people, still have to get a phone number. But that's just because, people don't, they're stuck in the old narrative. So let's review what it means to communicate. And this is the way to think differently. So this is a diagram of, transmitting a picture from one place to another. But the key thing is there's a boundary between the telecommunications world and it's sort of the world in which people are communicating. So we use the facility as a resource, but we don't depend on it because the image itself is assembled outside the network. The green line, that's the meaning is outside the network. This is a very deep concept, which I'm not going to be able to get into here. The meaning is not in the network, the packets are. It's a very different way of thinking. We assemble the image in our devices. But it gets more interesting because the meaning is not even in the picture. The meaning is in our minds. The meaning is in how we perceive the images. And we don't even need every pixel. We can, if you're missing a few, we can still recognize the image. You can look at a cartoon image and recognize who it is. The network does not know, is our purpose to transmit every detail of the picture, or is our purpose just to recognize who it is? There's more reason we have to solve things outside the network. And the meaning is actually in our minds. It's not in the images. So that's the challenge we have in trying to sort of support such connectivity. But what's interesting is we don't even have to transmit the pixels. We transmit the reference. We don't send Wikipedia. We just send a URL. We can send the name of a person, and you can see the image in your mind. Not a very good image, but what can I say? But this is really the problem you have when you try. Communication society tries to preserve every pixel. We don't need that. We might just need the name. So this has led us to a sort of a do-it-yourself implementation of connectivity. The original broadband was going to be a fat pipe with all these services built in. This is the policy transition. And the carrier provides each services. And the internet was just another connection within that. But with home networking, we start to shift the paradigm. With the NAT router, you now own the network in your house, and all those services come over that IP connection. Even now, like Verizon Video comes over IP. Increasingly, everything is just over IP, the generic connection. So the provider can charge for the services, and it becomes free to use. Now, what I mean by the term free to use is that, like sidewalks. Sidewalks are not free. They cost money. But they're free to use because we pay for them in a way that does not prevent us from using them. And I use the term ambient connectivity for this ability to assume we can connect, just like you can assume you have a sidewalk or you have grass you can walk on. So the next stage is do it ourselves. Basically, the same way TCP is a cooperative protocol, we can basically reinvent connectivity. This is what the internet really is about locally. We can pay for local facilities just like we pay for local roads. And the model of owning the infrastructure in a home, we can own the infrastructure, apartment houses, in villages, in estates. And telecom still exists, and that's actually wonderful because, as we said at the beginning, it's just another wire we can repurpose. And that creates infrastructure, I'm calling it, at scale. The scale being your house, your community, or beyond. Now, one reason this works very well is that packets are bursty. It's very different measures. It's not like water. So if we have a shared medium, I use the term pipe, which is a telecommunication model, 100 people sharing a gigabit, each think they're the full gigabit. Because when you're browsing a web page, everybody else can be using the facility you wouldn't notice. And that's thanks to the bursting nature. And if the web page is delayed by 1/10 of a second, I don't think you're going to get too upset. And the other important part is it's a fixed asset. You own it. You're not worrying about each time you're using. And this is necessary for connected things, for the Internet of Things. And there's little, basically there's little ongoing cost. And this is where it's starting to talk about opportunity. We create opportunity by providing people with a resource without dictating what they do with it. So let me just give one example of this in practice. And this is a real example. You might have noticed lions in the Serengeti carry collars with radios. They each have a GSM chip and GPS. Now, by the way, GPS is a wonderful example of a free-to-use service. The government spent billions of dollars on the GPS system, And they did it for the military. They weren't going to do it for civilians. They should pay their way. But because we, again, programmed around it, used it as a resource, we created billions of dollars in value. And this is part of the problem trying to explain infrastructure is people don't see the value until they have it. I mean, if you told the government, launch satellites, everybody can get driving directions, you would have got nowhere. But we discovered how to use it as a resource. Problem is, each lion needs a cell phone account. Now, it turns out telephone companies are nice to lions. I mean, who would argue with a lion? And they basically get free account. But the GSM protocol requires an account. They sort of say, okay, you know, it's not really, you don't really have an account, you can just use the protocols. But this is part of the telecommunications business model is these protocols, and 5G is even more so, designed to make sure that somebody gets paid for using a fixed asset because they want to pretend they're creating value. But the internet is like owning our own radios, just like I had that local example of local connectivity. So rather than services, we have a resource, including location, as I said. But now we can use those radios for other purposes because they're free to use. So cities could also provide traffic, weather, other free to use information. But one other example, now I used to use cows, but since I gave a talk in Mumbai, I switched the pictures to sheep. But I learned since then I should have shown goats. But we won't get into those details. But now you can use it for other things because you no longer have to worry about justifying the cost of an account for each animal. And the other important point is this is a local resource. You can own your local connectivity and build from there. This is not the internet out there. This is the internet here. But so, first policy lesson, be careful what you ask for. Broadband high-speed internet are the old model. You want to ask for local ownership of infrastructure. Network neutrality assumes somebody's deciding which bits are better than others, and what you really want is indifference. They shouldn't even know what the bits mean. They shouldn't even be able to be neutral and non-neutral. And rather than smart cities, you want empowering cities. You want resources that people can use to create their own solution. And the other big thing you want, and this is a long discussion, is APIs, application program interfaces. So if somebody just gives you an app, and I'll show you that, how do you build on it? How do you add value to it? So more internet is about economics, local ownership. And aligning self-interest unleashes Moore's law, because people start to build value on what they own and control. You know, as opposed to somebody making money by, you know, sort of when we went from the days when you had time sharing, you paid to use a CPU, to when we owned our own CPUs, a wonderful innovation. Unfortunately, the cloud is back to the old model, but at least it's cheap. Okay, now in India, there's a whole fight over free basics, which is another discussion, but very simply, it's the old model that basically telecommunications decides how much each service costs. So Facebook is trying to create a free service for a subset of connectivity because they assume pipes are expensive and everything. So they're trying to make sure that only low impact applications are available. And personally, I think it's a noble effort, but it's still the old telecommunication model. So I think it's a good thing as long as you don't confuse it with the internet. So okay, I mean, basically, I'm emphasizing the points here, so I'm going to skip over this. So the main thing is to understand the concept of software's programming around it, which is a theme here. And the importance of architecture, the ability to basically decompose a problem so that we can concentrate, and we're going to talk about the Internet of Things this afternoon, on connected things, rather than on all the stuff between. It also means that, the Internet of Things, if you have, lights that turn on, I don't want just an app in my phone that can turn it on. I want to be able to basically write my own applications and build on it so I don't have to wait for standards if I have APIs that allow me to use software to discover my own solution. But we have to be careful about narratives. The current narratives of telecommunications, of the web, of services, access to the internet, are the old narratives. And then there are other topics, you know, DC power and USB-C are starting to apply sort of some of the same dynamic to the physical world. But again, there are a lot of deep topics we can get into. In the meantime, anybody's questions? No? Okay. Anybody awake?
You're saying that it's old thinking of the current infrastructure model. What is your preferred suggestion for an alternative to what's currently used as the basic infrastructure? Are you talking more about going to a MeshNet?
See, but that's the important point. Were you here for Peter Hotty's talk yesterday? The answer, it doesn't, or not Peter Hotty's, Scott Jensen's talk. It doesn't matter what the physical infrastructure is. What's important is the economics, that if you have a free-to-use infrastructure, that enables the innovation and connectivity. But the importance of the architecture is that you don't worry about what's on the other side of that architectural line. It's just stuff. And meshing is a technique. Wi-Fi is a technique. None of them are critical. You don't have a separate wired internet or wireless internet. It's just a technique. So this is why I'm talking about local ownership as a priority, economics a priority. And the protocols, current internet protocols aren't that great, but I can program around that. And that's really the theme here. I can create application protocols. And if you look at the example, and I've got a longer talk on that IoT example. I can talk about how I programmed around things. For example, it's in my house. How do I get to a device inside my house with current protocols? Well, there's IPv6, which might work. It has its own issues. But so what I did was port forward on a separate network connection to connect to that device. Now, that's really dirty because I have to know enough to control the NAT and everything to forward it. But maintain the architectural integrity. And this is my next comment about. In other words, I'm willing to do kludges, but they've got to be in line with the architecture. So as I clean things up, as I improve things, as I make them smoother, anything relies on the architecture will continue to work. And anything that I improve inside the network basically will improve it for everything. In other words, if I make connectivity smoother or less expensive with packets, everything improves. Whereas if I just made voice a little better, you get one particular service to improve. And that's really part of the magic here. Any other? Okay, if you want, we can return to the snow area in progress. Actually, apparently there is a storm back in Boston today. Oh.
Well, since we're just
Yeah.
BS in here, you know, you're talking about the origin of the internet and all that.
Mm-hmm.
So I went to a fireside chat with Larry Roberts.
Yes, and I'll probably disagree with him.
But, well, I mean, he gave at least the anecdote of how they invented packet stuff.
At UCLA?
No, at ARPANET. I mean, no, that this concept came by that I mean, the whole project how it came up. Like you said, the stuff happened by accident. What he said was that he said basically he just wanted to essentially fax something, right? From one room to another, or calling or something like that it is. And so that's
well,
short where the packet concept came from. It was really just for a little science experiment, just for the hell of it type of thing, and that was where.
Well, I think there are a couple of origins. I mean, this probably is in line with the Kleinrock story at UCLA, where Kleinrock but Kleinrock was trying to preserve a lot of the old telephone network to show that you could do a telephone network using packets. There was also, I think, Neil Davies in the UK did work with packets. So there was some work, and in the commercial world, we had terminal networks where instead of packets, we had characters. Your terminal, you type a letter on a terminal and it get transmitted, to the next thing. So we built terminal networks. So there was a lot of this experimenting going on. The ARPANET was best known because the government used it to pull together the research computers. But this is why the discontinuity is not so much packets. That we had packets. It was the acceptance of best efforts, the fact that you can lose packets of the network and had to take responsibility outside the network. Cyclades came close. It was a research network in France that was a packet network built on unreliable nodes. But the interface it presented to the computers on the outside was a reliable interface. The big idea here was to say, we're going to present an unreliable interface to the applications and let them work it out. And that's why we also have UDP, which uses a datagram protocol where you just throw the packets in and you have to take responsibility. You don't have the TCP library.
Well, yeah, and the only reason I brought it up is just that I was
No, it is. I mean,
just to make it clear, I'm certainly not making any point to who invented.
no, I know. Don't worry.
It was what ARPANET.
No, Larry definitely played a role. No, definitely played a role in there and helped figure out the ARPANET.
Actually, when you comment on one, you think, and I don't, I'm an expert in that area, I don't understand fully, but one thing you said that was really key to that was the packet size and how it was limited to, I forget, whatever it was originally. But, I don't know.
Well, the packet size, basically with dial-up, you didn't want a packet that was too large because it was like a train, and if the packet was too long, other things get delayed. But now, packets are, when you have a gigabit network.
Sure. But I mean, like Twitter, right? I mean, now it gets to that. There seems to think there's some kind of, magic thing about the particular. Of course, barring that they just announced they were thinking about.
Yes. No, the thing about Twitter, and I'm trying to figure out how to close this PowerPoint. It doesn't want to close.
Apparently, it's not just using it for what it's doing.
What?
It's apparently giving you a presentation.
No, I know, but that dialogue, I said resume slideshow, it doesn't want to continue. Oh, there's a dialogue, yes. It's on the other window. How do anybody see? Are you right? Okay. It's so embarrassing. Okay. Now you can all cool down. But no, sorry, I didn't mean to get distracted. No, I appreciate there are a lot of people contributing. One of the other interesting things about the history is one of the two key people, J.C.R. Licklider and Bob Taylor. They're both acoustic psychologists. They were not computer people as such. Acoustic psychologists. How sound is perceived. And when I started psycholinguistic class, I ran into a 1949 paper by Licklider on taxi radios in noisy environments, and how some of the clicks and some of the things you think are bad actually make it work better in noisy environments. So this is important in the military when you're in planes and noisy. So this is, some of the goal was man-machine interaction. It was basically to give people, tools to work better. So it wasn't so much the technology that was driven it was this need to communicate, need to work together. No, psycholinguistics.
Oh, okay, sorry, I misheard.
Now, Worcester is another city.
I went to school there, that's why.
Oh, which school? School? WPI? I was about to say WPI, yes. A good school. Yes, but yeah.
What are you trying to skip over around school?
Thank you.